So hi, my name's Chris. I'm the VP Engineering of Ordinate, as you just heard. And today I'm here to give you an overview from a very high level of some of the basic concepts of networking and try to give you a language and a vocabulary that you can use when you're talking to the IT pros who are on the job or you're involved within any kind of installation. So we call this Networking 101. We're starting at a very high level. It's there, so for some of you, you may know this stuff, I apologise, and for others it may be the first time you've heard it. So I'm trying to walk a line here and try and find a balance where everyone gets something out of this. So to start off with, IP networking, it's pervasive, it's everywhere. It is the internet. So if you have one of these, or a set-top box, or one of these, which everyone has, you use it. You can't avoid it. Phones have been using voice over IP for forever and a day. Even when you're at home, stuff that is now in your home is all networked and you don't even realise it, or you didn't realise it at the time. When we go to audio over IP, people don't even realise this. They use audio over IP all the time. I've already mentioned VoIP, and VoIP has been in phone handsets and in the carrier network for a very long time. Services such as Pandora, Spotify, Skype, they all use audio over IP type technologies. So why? Why do we use IP networking? Well, first of all, we'll answer a different question that we need to get to, which is why you do digital to start with. And that's really, in any case, despite arguments you might use, any kind of digital transport generally is going to allow you to reduce the amount of copper in the system. Whether it's networked or not, it doesn't matter. So you get rid of the big, heavy multi-cores and you can replace them with digital transports. So when it comes to networking, we've got this thing that's part of it. It's called the digital transport. It's how we get the digital stuff around. Well, there are lots of different types of digital transports, and some of them that are not networked, they all have this same characteristic where you can get multiple channels of audio and video, or whatever you're doing over the link, down a single cable, sometimes in both directions. So some examples: SPDIF, that's been on the back of a computer for years. ADAT, that's one of the oldest optic fibre type technologies. AES3, I'm sure everyone has used AES3 at some point, somewhere. And that has become really quite pervasive. So when it comes to networking, if you combine these with the power of a network, where you have this n-squared type explosion in the number of endpoints and the number of ways you can do things, you're allowed to now send signals anywhere, flexibly, easily, using very, very simple methods, without the copper. It's that simple. So an example, imagine we had two devices, we want to send some audio between them, and we'll just use a cable. Start off with an AES3 cable, for example. If I want to send some back the other way, I need another cable. I want to add another device, I need some more cables. And I can only send audio along those paths. As I add more devices, it starts to become very, very, painful. With a network, you can do all of that with just the one plug, and then using the network to route the signals around. So it makes your life a lot easier. Now, IP networks are, fairly complex things when you look at the details, but at the high level, they're really quite simple. They're packet switch networks. They break the data, the stuff that you care about, they break it up into these chunks called packets. And those chunks get sent through the network, switched off towards the destination, who puts it back together and then sends the data up to the application that's receiving it. It's really very simple at that level. The switches in the network are the things that forward and send the data on. They decide where it goes and they make all the decisions for you. These messages need lots of stuff attached to them in order for them to know, where they've got to go. So they're wrapped in what we call headers. It's like, bits of stuff that get stuck on the front. And you'll see lots of pictures, that sort of have this kind of stack thing, here, where you've got the data that you actually care about, and then, headers, stuff that's stacked on the front that's extra data. And when we draw them this way, we always draw the data as being really small and the header as being really big, because we don't care about the data, we care about the header. Like, I'm a network engineer, and the header's tiny, and the data can be up to whatever your link will allow. So It's overhead, but it's not very much. Okay, so don't make that mistake. We call this encapsulation. It's basically like putting a letter inside an envelope and putting some information on the front of the envelope, and then putting that envelope inside another envelope and putting some different information, and using the the unwrapping process of the envelope to decide what to do with the next layer. So that's a very simple way of visualising what this actually does. This is often described as layering, and so network engineers and software engineers use this principle everywhere in the way we work, and you'll see this everywhere. You've already heard Roland refer to it, layer 2, layer 3. Hopefully today we'll learn a little bit about what that means and how it actually relates to what you're trying to do. What this principle gives you is the ability to run multiple services over one cable. I can do different things over that one cable. And the classic example at home, you've got your home network, you've got your Wi-Fi, so you might stream stuff to your Apple TV, your phone, etc., etc. They're all different services running over that one network, and they rely on layering to make that happen. So I've started using a bit of vocabulary and a bit of sort of jargon, and so the point of this presentation is to give you some pointers as to what some of this jargon means, and actually give you that vocabulary you can use when talking to an IT professional. So just to hammer home the layering thing, the OSI model is a thing that you may have heard of. It's a fairly academic, abstract thing, but it's actually a standard, and it's a standard set of nomenclature for how you talk about breaking things up inside a network. It was put out by the ISO. It's well more than 20 years old. The second revision is 20 years old, and it's used by everyone everywhere when they're talking about concepts in networking. So, it's a layered stack thing, has 7 layers, starts at the bottom, works its way up to the top. Data comes in from the top, makes its way down, across, then back up the other side. Okay, so as you go through, you layer it up, then you unpack it. Now, if you were to sort of jump onto Google to look for a better picture of this, your brain would explode. There's like 1,000,005 ways of describing it. Hamburgers are really popular. And so are circles. I don't know why, but they do. They like circles. Second piece of vocabulary, CCNA. Is anyone here a CCNA? No? There's one. You have one? Okay, all right. It's basically a license to do damage. It's a certification that you go through. Cisco offer it, and it gives you the skills that you need to drive a network, basically. And so people who undertake the CCNA or the Cisco Certified Network Administrator coursework learn a lot of skills about configuring a network. And they're useful people. As much as I say they do damage, they actually do good things as well. Just don't do everything they tell you. All right? So CCNA for Dummies talks about layering. Okay? And here's an exam question for you. There's an answer for it. 3 reasons why you want to use layering. Okay? And there's a lot of words here, but what it's basically saying is that it allows you to break things down into sizable tasks that can be done in isolation. So I can do this one thing and not worry about what happens next. Once I've done that one thing, I'm good. Then I can do the next thing and not worry about what happened before me or what happens after me, and I'm good. And so if you're an engineer, you're designing something, you like to work that way, right? It's nice to break things into small, manageable pieces. That's what layering does. So it describes the OSI model as data communication components that are independently defined, and that's it's a nice, succinct way of saying it. So remember that for your exam. Can be viewed as a stack, and there are hundreds of different examples of this. Why is it shown this way? It's probably just because it always has been. The first person to draw it did it this way, and it's just stayed that way. I don't think there's been any significant reason to change it. From a developer's and an engineer's point of view, it's kind of useful. It gives you a framework. And so that's about the language and the jargon. At Ordinate, we like to think of it as an onion. And when you think about the layers inside an onion, as in, encapsulating in and out. So layer 1, what does layer 1 do? Well, there are lots of ways of describing it, but it's basically the cable. Okay, so the technology that gets the bits over the cable. Cat 5, 6, the physical layers of Wi-Fi, 802.11a, 11g, 11n, 11AA, they're all things that you've heard of. They're wrapped up inside Wi-Fi. Fibre optic is another one. I've mentioned some of the RFs. And it covers the way that you get the data encoded on the wire and understood at the other end and turned back into ones and zeros. And so it's a fairly complex part of the system that we don't really need to talk about today. It's kind of where I spent a lot of my time studying. I love it, it's great. It's very mathematical, it's very, there's a lot of stuff that goes on here. But for our purposes, it's like, am I going to use fibre or am I going to use Cat 5? That's kind of the decision you've got to make. So this one is quite different to the other layers because it does involve, manipulating bits and, words like Manchester encoding or OFDM, if you've heard of those. They are physical layer concepts. And it's all the bits. An audio technology that kind of uses a layer 1 type approach where it effectively is just a bit signalling mechanism. A good example is AES50, which is mostly a layer 1 technology. They send clocks down wires, they send bits down wires. That's basically what it does. It's the brown bit on the outside of the onion, it's the brown skin that you take off and throw away. But you rely on it, keeps the onion protected, make sure everything gets there, it's all kind of good. So that's enough on the physical layer. Come talk to me later if you want to learn more. So if you slice the onion vertically, the lower layers are like the outside of the onion, so the outer layers. And then as you get closer towards the middle, that's basically getting towards the data. So you're going up the stack, you're going into the middle of that onion, so layer by layer. And there's a nice graphic to help you visualise it. So it's kind of useful as a construct. We found this when describing it to people who hadn't come across these concepts before, because if you look at this picture, it's kind of just a bunch of squares and rectangles that have words in them, and they don't have a lot of context or place or meaning. But if you're thinking about it in this context where you're literally peeling away, it starts to make sense. So let's move on to layer 2. And this is what we call the data link layer or the media access control layer. You'll heard MAC, that's a very common phrase. And this is where Wi-Fi gets its name. It's the MAC protocol for Wi-Fi. And it's the lowest layer that actually deals with getting the data across through the physical layer. And so it's a logical layer in that it puts a header on devices. It's that outermost wrapper. It's the outside wrapper on the encapsulation, if you think about the onion. And so it's down in here. And so it's basically the bit that gets taken off by the hardware when you receive a packet. It makes sure that data gets there reliably. So over Ethernet, it's responsible for detecting errors. If there was a cable, a bit error on a transmission, it's the MAC protocol, layer 2, that's responsible for finding that and saying, throw the frame away, because you don't want to send error data. In Wi-Fi, it's responsible for retransmitting the data. Wi-Fi has to, because it's wireless, things go bad. You have to be prepared to send something multiple times to get it through. That's the job of the data link layer. And it's where you start to build up the concept of a local area network. Okay, so it has the ability now to start to put multiple devices together because I'm sending something along the wire. As far as networked audio over IP, Dante is concerned, 802.3, Ethernet is kind of the king of physical layers. MAC protocols, that's the one we like to use. It's fantastic. Ethernet likes to use the word frames. IP likes to use the word packets. They're the same thing, they just have different words. And what it is basically a collection of data, header, stuff, right? It's stuff that the network uses to get the message through. So the media access control protocol, how many of you are I've been working in networking long enough to remember the Ethernet that was the coax Ethernet, and you used to have collisions and stuff. Yeah. And as you start to add devices, it'd sort of fall off the cliff and stop working, or the cable would go around the room. Nowadays, with Ethernet, things have advanced so far that you could not recognise a modern Ethernet system if you looked back at a CSMA CD system. They're just not the same thing. And it's part of that, that evolution of technology that goes on. And it happens at this layer because things get faster and faster and faster and more capable. And the thing that made this possible is the introduction of the Ethernet switch chip in silicon. That was a big thing. It relied upon information that's in the Mac to make it work. So it has the concept of addressing. A MAC address, which you've probably heard of, if you've used a network, you've probably heard of a MAC address. It's unique to every single piece of hardware on the planet has a unique MAC address in the Ethernet world. And that's important because you can plug then any Ethernet device into any network ever, and they'll never collide. That's a huge thing. So these addresses get used by the switches to make decisions about where the packets go in the network. And so it's, we're starting to build up the concepts that you need to be able to actually network and get a message from one side through some complex set of switches to the other side. So what about audio systems that use layer 2? You've probably heard of CobraNet. It uses Ethernet frames. You've probably heard of EtherSound. It uses Ethernet frames too. And you've probably heard of AVB. It's based on Ethernet frames as well. So they're very low level, which means at the software level, I'm talking to a device. I'm talking to a device driver. Okay, so it's it's a low level thing, but they rely on the fact that a layer 2 network can get those packets through and make the job of getting the audio to the other side possible. One of the drawbacks of doing this is that it's very difficult to scale. So once you get to a certain point, you've probably all experienced that CobraNet systems start to become very complex and difficult to manage. So do AVB systems, so do EtherSound. They all have issues with scaling, and that's a fundamental issue with layer 2 protocols like this. They don't scale very far, comparatively speaking. On the internet scale, they don't scale very far. On the hotel scale, they might, but on the internet scale, they don't. So that's where we start to look at layer 3. And layer 3 is kind of the granddaddy of all of these areas in the protocol stack. And this is where people start to feel like they're on familiar ground, because you actually interact with layer 3 in your computer every day with your IP address, or getting an address. I haven't got an address. I can't talk to the world. That's where you're starting to interact with the layer 3 solution. So back to the onion. It is the IP header, the IP stuff. These are IP packets that we're talking about. That's what layer 3 is responsible for. And it's the aggregation of stuff that lets you put together like a big scale network like the internet. It's the stuff that the network needs to connect smaller LAN-sized networks together. And so that's what an IP address is for. Breaking up data into sizable chunks, so that it can be managed over different link types. Maintaining some other things like type of service, which is for, do I treat this packet specially or not? Do I do something with it? And so, it's very useful. IP addresses are the thing that you will interact with most often. I'm sure everyone has been into this dialog box at some time or another in their life and typed in some numbers and wondered what it meant and wondered how it worked and wondered why it didn't work, more importantly. Some detail on how IP addresses actually work. They have two parts. One's for the network and one's for the actual device, or the host. They use the word host to describe an IP host. So if you look at 192.168.25.100, it has this little bit of extra information alongside it. That's called a net mask. And that's really important because that lets you work out where the network address is and where the device address is. And so without the two of those, you don't actually know how to break this apart. And that's why if you don't enter a net mask, things don't work. Okay, so it's actually an important part of the system. Now, IP addresses are managed things. You have to buy them. They're managed by a group called IANA, Internet Assigned Numbers Authority. It's basically a big spreadsheet. It's quite large. And it took an old school approach, which was to divide the IP4 address space, IPv4, everyone sort of heard, that's what people are dealing with today in those interfaces. They broke it up into fixed sizes as fixed chunks. And so you've probably heard Class A, Class B, Class C. And what that's doing is really taking different net mask sizes and different network address sizes and saying we'll have a big address, a big pool, a middle one, and then a smaller pool. So as you go from C to B to A, you can progressively have more and more hosts on the network and less networks. So that's why a Class A address is a primo commodity today. To buy one is very expensive. There are some special addresses in there, private ranges, so addresses like 192.168, you've all seen that one I'm sure, 10.00, 172.16. 192.168 is a Class C or a Class B private address space. 10 is a Class A private address space. I'm sure you've seen the 10 address space used everywhere. It's used by most enterprises on the planet to address all their computers because it's the only way you can practically do it. This is a slightly more advanced topic, but everyone's heard about the shortage of IP addresses, and that's why we're doing this thing called IPv6. And that's kind of a difficult thing to do because it's a boil the ocean strategy. It's like we've got to replace IPv4 with IPv6, which means that every router, every endpoint, everything needs to be updated for it to work. And that's been a slow process. It's happening, and right now carriers use IPv6 and you don't even know it. But you're still using IPv4 on the edges. And what got us to this point, and why we didn't cross this kind of threshold many, many years ago, is this thing called classless inter-domain routing. And what it did was allowed you to make the network addresses variable size. So I don't want it to be a Class A, I want to make it a little bit bigger, or I can make it, bigger again and bigger again. And it allows you to create any size network out of that same address space and do so in an interoperable way. And what it does is it changes the way that we talk about things from having a blah 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 /netmask to this /24 or /8/16. And if you've seen that, what that's saying is we're using CIDR and we're defining a Class A, a Class B and a Class C address space. It's really, really useful. Now, you can set IP addresses manually, statically, or dynamically, when the computer boots up or when the cable gets plugged in. Static requires someone to do some work and to keep doing some work to keep it maintained. It's error-prone, it's time-consuming, and it's a major, major cause of support calls because there are multiple addresses, they're incorrectly configured, someone's put the wrong number in the wrong place when they've typed it in, etc., etc. A much, much better solution is looking at doing this dynamically, and then there's a protocol and a system called the Dynamic Host Configuration Protocol and Control Protocol. And what that does is allows a device to come up and see if there's a server and say, hey, I need an address, and if it gets one, it's all good to go. This gives you a lot of control, and for a system admin, it gives you a hell of a lot of control because you can now go and to your server in one place, you can write down all the ways you want to assign addresses. You can do, certain devices always get the same address. You can do certain groups of devices from a certain IP address range. You have total control, and it's in one place, and the administrator has that. So the chances of error here are far smaller than they are with static addresses. But what about if there's no DHCP server? What do you do then? This is where a relatively new on the IP scale piece of technology comes along. This is called IPv4 Link Local, and we use this in Dante extensively. And it's the bit that makes it plug and play, where you just plug it in and it works. It's about self-assigning an address. And they use a special range, and devices go through this whole process of coming up with an address. It's supported on OS X, Windows, Linux, everything. iOS, Android, they all do it. Dante devices all do it as well. very, very common. They use an algorithm to say, hey, I think I want to use address X. And so they go out in the network and say, is anyone using address X? And if no one answers, they say, cool, that's me. If someone answers, they go, I'll use Y, etc., etc. So it's a completely baked in, simple way to get your system up and running. And so that's what we're doing here now. Just plug stuff in, it works. There's no DHCP server, there's no configuration required. It's all automatic. So the IP header has lots of stuff. It's useful stuff, and it's the stuff that a router uses to connect networks together and get packets across the internet. I wouldn't even begin to try and explain what's in here apart from to say it has addresses, it has lots of other stuff that's really useful. So layer 3, in the information that's in that header, enables routing of data. Now the line between routing and switching is becoming blurred, but routing is how you connect networks together. And it's what makes the internet go, it's what makes it scale. So if you create networks and then want to connect those networks together, you need a router, and the router uses the IP addresses to connect connections between endpoints. Layer 3 network examples, my favourite, Dante. AES67 is a layer 3 profile of a whole bunch of layer 3 solutions. So the QLAN and QSys and Ravenna and all the others fit in this same category. We use RTP in the AES67 solution. That RTP is a layer 3-4 solution. All of this information, some bits of it that I've said in there are useful, and some bits are just sort of informational, and it's hopefully about giving you some background. But these 3 layers that I've spoken about here are, in your day-to-day use of a network, the most practical and the most sort of the places where you actually go and interact with the network. And beyond that, there's not very much that you get to do. We'll run through it a little bit just quickly. Transport, layer 4, that's TCP. Everyone's heard of TCP, I'm sure. That's how you connect to a server. And again, it's sort of in this point. So we're getting closer to the data now. We're really, we're getting in towards the middle of the onion. It's responsible for a lot of stuff. It makes sure that the data arrives. If you're sending data over the internet, it can get lost. It does happen. So TCP makes sure that it arrived, and then if it hasn't arrived, make sure another copy of it gets sent. So therefore, it has to also deal with 2 copies of it arriving. It has to deal with packets coming out of order. So it's 1, 2, 3, 4, they're sent. You get 1, 3, 4, 2. It puts them back into order, and so that the application doesn't know about it. It happens all the time. And it's also responsible for making sure that the network doesn't collapse and everybody just sort of send stuff as quickly as they can. It's called flow control, and it's about just putting a bit of a pause on how quickly you start transmitting packets onto the network. And that's incredibly important in keeping the internet stable. TCP is a genius piece of engineering, if you ask me. UDP is another transport protocol. We use this in Dante extensively. It's lightweight, has very little information attached with it. It's literally just like a post office box address. It's like, there, thank you. There's no retransmission, there's no flow control, there's no nothing. It's good for streaming media because the application dictates how much media gets sent. So if you're thinking about an audio stream, that's going to be of a given size. We can safely use UDP because we know that we're not going to send any more packets. Anything that's layer 3 audio is actually using all of the layers, by the way. We talk about layer 3, but it's really a full solution. And by that I mean layers 5, 6 and 7, or 4, 5, 6 and 7. And to use, because I know about it, Dante, the Dante examples. Layer 5, how we start and end a conversation. That's the stuff that makes when you click in the Dante controller and it starts, and you click again and it stops, it's that stuff. TCP is actually both layer 4 and 5 because TCP starts and stops connections. Layer 6, that's how the data is treated. So that's sort of a good example here is in your web browser. If you use an SSL connection to your bank website, you'll see a little secure thing come up in the corner. What this is doing is saying between the endpoints, this data is not what you think it is, it's something else, and here's the information we need to make that work. So that SSL encryption is a good example. Everybody uses that every single day. And then the application layer on top. That's the audio, by the way, in Dante. In layer 6, that is the way that we decide what channel is going to be where and what packet and how many samples and all that kind of stuff. It's how we structure the data, to give the Dante example. And yeah, layer 7, it's the contents of the web page. It's, you know, the stuff that you actually care about. So some other networking concepts that we need to quickly look at: Unicast, Multicast, and QoS. I'm sure that everyone's heard of Multicast as a thing. It tends to be a big topic in networking. Unicast is really useful for point-to-point. So this is replicating a cable. You know, I'm sending to someone at the back of the room. That's a Unicast connection. It's very, very good for point-to-point signals that need to go from one place to another place, or to a small number of places. Multicast is really useful for sending one signal to many places. So that might be, you know, a feed out to a whole batch of amps, for example. They're all basically amplifying the same signal, multicast it to them. And the little graphic here shows you how that happens. How does that actually happen? That's a good question. Well, Unicast is based around efficiency. All right? I only send the audio once, it goes to the receiver, and it takes a really, really clear path through the network. It only goes on the path that it needs to take. So if I've got, you know, the 3 or 4 ways that I can get from one place to another, that audio will only take one of those paths. And so in this example, the sender and the receiver go through one switch, and here the sender and receiver, they go through 2 switches, but these guys up here don't see any of the traffic that's coming from down here. It's the way Unicast works, it's the way Ethernet switches work. And when I was talking before about coax, this is a huge advancement in Ethernet, and this is what makes Ethernet go fast, what makes it reliable, and what makes it basically as good as a cable. Because there's no contention anymore, unless there's lots of people trying to get out one port. And even then, that's why you have QoS, that's why you have other techniques to handle this. And never ever underestimate the ability of the people who drive Ethernet, the IEEE, to make it go faster. They're just going to keep doing it. They've been doing it all my life, and they're going to keep doing it forever. You know, 10, 100 gig, 10 gig, 40 gig, 100 gig, etc., etc. They get cheaper and cheaper and cheaper every year. And there's nothing that you can't do with more bandwidth. It's the best solution for everything. So when we come to multicast, we have to get that signal to lots of different receivers. And this is where the switches come in again. And the switches are used to replicate that data and send it everywhere. And so that data actually floods through the network and goes out every port. So when you're designing a system or working with it, if you're going to make something multicast, you should assume that it's going to go everywhere and everyone's going to see it. And so you're going to see those packets and that bandwidth on every port. And if you compare it to Unicast, to achieve the same thing that I'm achieving in this top diagram, where I would send one packet and it would go to 3 people, down here I would have to send that same packet 3 times. And so if you scale that up, you can suddenly see why multicast becomes a useful feature. It can also be dangerous in that it goes everywhere. So there's a thing called IGMP you might have heard of. This is again a piece of language that you can use when talking to a system admin. And this is a mechanism for the network to control where that multicast goes. And this is useful if you care about having a lot of multicast on the network and making sure that it doesn't, cause problems. So it's an example of where a switch does something intelligent to help determine where the audio should go, or where the packets should go, sorry. And so that, again, if it's enabled, will help greatly. All stacks, all IP stacks use IGMP by default. Dante devices do especially. And so if it's enabled in the network, it will help to control your multicast. Quality of service. Now this is a big topic, and I don't want to go into it too much today other than just to mention it, but quality of service has a hell of a lot of words associated with it. It's a really complex, big topic. What it's about is trying to mimic, what airlines do, Group 1, Group 2, Group 3 boarding, that kind of thing, priority lanes in traffic. And it's about making sure that the important traffic gets high priority treatment and the less important traffic gets lower priority treatment. It's usually achieved by putting some information in a packet and saying, hey, this is important, or that's not important, and then letting the network deal with it. It's been used by voice over IP for years and years and years, and so it's well baked. It's been in switches and everything for a very long time, and it's part of the system that helped enable technologies like Dante to become effective on 100 megabit networks. This was really essential at that time. Less so on gigabit, even less so on 10 gig. You'll see a word, diff-serve code point. It's a piece of jargon, DHCP. It's an important number. You don't need to know what it means other than to say, I need that number to say this. And if you do that, it works. It's called diff-serve. That's the word. It's a piece of information in the header of the packet, so every single packet has this information in it, and switches use it to make decisions about where those packets go. As I said, it's used in VoIP today. Now, switches can do lots and lots of different things with this. We like to keep it simple and say that, if you're going to deploy QoS, you want to make sure that you're really only doing, high priority and something else. So for us, that means audio is in the something else category, not high, and clocking is in the high priority. Okay? You want to keep your high priority classes like your galactic class frequent flyers. You want to keep those numbers small so they can have a fast path through. There's a thing in here called strict priority. It's a word to remember, and what that means is you always serve the highest priority first. So if there's a packet waiting in a queue that's highest priority, it goes first over everyone else. There's no fairness, there's no waiting, round robin or anything like that. It's, no, you first. So now that I've spoken about a whole bunch of jargon and lots of words there, let's look at how we might use some of these words in real scenarios where you're actually trying to deal with an IT person. And how that affects your deployment of a Dante system. So if you're going to add audio, networked audio, to expand or replace an existing, say, common use network or dedicated infrastructure, then you're generally dealing with an IT person because they're going to own it. So in this hotel, for example, they'll have a common IT network. It's going to serve the cash registers. It's going to serve the security cameras. It's going to serve all sorts of things. And Dante is networked and can be run over that same infrastructure. So it doesn't require special infrastructure. Because of all this stuff I spoke about before, about using standardized approaches, we can operate alongside all the other standardized things like voice over IP, like video, like web browsing, like all the other approaches that are out there for getting data from application to application. Dante does it properly. It does the right thing. And so switches and routers and firewalls and all those things know what to do, and the IT admin knows what to do with it. We use DHCP addressing. Dante uses DHCP addressing, so it will automatically get an IP address. Okay. Some devices allow static config. That's a manufacturer-specific thing because they can turn this on and off, and only some have turned it on for various cases. But by and large, Dante devices will configure themselves by DHCP first, and if that doesn't work, they'll use the link local approach that I spoke about. So talking to the IT means having a conversation about using DHCP. We use some other protocols to help with discovery and finding each other, etc. And these are standard internet protocols that your IT department will know about. It's just what Apple used to call Bonjour. And it runs on your home network, it runs everywhere. It's very common, and the IT department won't be fazed by it. We use a standard protocol called IEEE 1588, PTP is the other word for it, and that does clocking. And that's the one I said was in high priority. And this is one area where, if it's a busy network or if it's a 100 meg network, then talking to the IT department about making sure that the clocking is in high priority is important. It helps to make sure that the thing goes smoothly. Again, it's very standard. It's just like they do with VoIP today, because guaranteed the IT department looks after the voice over IP phones. They know about this. We use UDP, so they'll see lots of UDP traffic on their network, and you can give them information about what type of or what rates of UDP traffic they should be able to see. Network engineers and network administrators like to know how much traffic there's going to be, and with Dante you can calculate that out to say, I've got about 5 megabits per flow, and I've got about this many channels, and it's going to be roughly this number. And that's not a very complex calculation to make. When would I want to use multicast rather than unicast? This is an area where, again, where IT departments will care. Using multicast is something that they tend to say, well, hang on, I don't like multicast going everywhere. What have I got, what are you doing? And when, it's like, I use IGMP, it's okay. And they'll relax, they'll be fine. And it won't be a problem. Again, this is another area where a conversation helps. And you can tell them that Dante uses IGMP. And if they have IGMP enabled, then it will be fine. And we basically use, as I mentioned, for the clocking protocol, standard VoIP quality of service. And we have a table that you can give to your IT department that says these are the numbers that Dante likes to use, and they can use them. And they can even get fancy with those and actually do some remapping or whatever they need to do to integrate it into their network. So it's a very useful piece of information for you, and it's a very powerful piece of information for the IT department. It's important to know that they're using DiffServ, because that's the version of QoS that we use, strict priority, etc., etc. The secret with QoS though is it's not really needed until you get to about 700 to 800 megabits per second. Before that, it doesn't really make a difference. If you're using 100 meg Ethernet, it makes a difference from the start. So it's important to have it for 100 meg, but for gigabit, relax. That's the power of bandwidth. 10 gig, you don't even need to care. So Dante is going to tag those packets, and the information it's going to tag them with is in this table. This is on our website. It's in our support information, and to an IT admin, this is gold. They'll go, oh, fantastic, thank you. That'll be awesome. That'll be all, and you'll be on your way. So hopefully this sort of rather long set of slides has been able to give you an overview of some of the words and jargon and things that you're going to need to be able to use when talking to an IT department in an installation. So if you've got any questions, come and see me afterwards. I'll be around for most of the day, and thank you.